Hello students, we are dealing with the unit number 5 of our M3 syllabus, that is functions of complex variable differential calculus part. In the last video lecture we have seen what is complex function, what is the definition or the concept of limit, continuity and derivative of functions of complex variable, that is f of z. Now we are going to discuss the very important topic from this unit, that is analytic functions and Cauchy-Riemann equations in Cartesian and polar forms. So this topic is very important from exam point of view. So first we will see the concept of analytic functions. Definition: a single valued function f of z is called an analytic function if f of z possesses a unique derivative at every point of the region capital R. An analytic function is also called as a regular function or holomorphic function. So these two are the names used for this concept or the function type, analytic function. Here it is important to note that the function should be a single valued function and it should have unique derivative at every point of the region R. This is the region R in which this function f of z is defined. A point at which the function is not analytic is called as a singular point. So singular point means a point in this region R at which this function is not analytic, means it is not possessing a unique derivative at that point. That point is called a singular point. A function is said to be analytic in a certain domain D if it is analytic at every point in that domain D. So this is same as the continuity in the region R of the function f of z. So on the same parallel line it is said that if the function is analytic at each and every point of the domain D, then it is said to be analytic in that complete domain D. Now let us see the necessary and sufficient condition for a function f of z to be analytic. The necessary and sufficient condition for the function w equal to f of z, which is given by u of xy plus iv of xy, to be analytic in the region R. Note that w is a function of z and it is nothing but the function of two real valued functions u and v. These two real valued functions are the functions of real variables x and y. So here in all, four variables are used, that is x, y, u and v, to write a function f of z or w. So let us see the conditions. Here you can find the four partial derivatives of these u and v functions, namely ux, uy, vx, vy. So these four partial derivatives should be continuous functions of x and y in the same region R. And the second condition is very important, which is known as the Cauchy-Riemann equations in Cartesian form. So this is very important condition. Using this condition, you can find the constants if the given function is analytic. So the first pair of ratios is ux equal to vy, that is dou u by dou x equal to dou v by dou y. These two derivatives should be having same value and the middle pair of derivatives should be with negative value of each other. So dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. If these two conditions are satisfied, then you can say that the given function f of z is an analytic function in that given region R. Now let us see the Cartesian equations in Cartesian and polar, Cauchy-Riemann equations in Cartesian and polar form. First in Cartesian form, if w equal to f of z equal to u of xy plus iv of xy is a given function of z and u and v are the real valued functions of the real variables x and y, then Cauchy-Riemann equations in Cartesian form are given as dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. The same you can write in short form as ux equal to vy and uy equal to minus vx. Now in polar form, if the function is defined as a function of z equal to u of r theta plus I v of r theta, here instead of the x and y variables in Cartesian form, r and theta are the variables. So in this case, the Cauchy-Riemann equations become dou u by dou theta equal to minus r dou v by dou r, and dou u by dou r equal to 1 upon r dou v by dou theta. The same can be written as u theta equal to minus r dou v by dou r, that is vr, and ur equal to 1 upon r v theta. So you should remember these two results, that is CR equations in Cartesian form and in polar form, while solving the examples from this topic, that is analytic functions. Also, in case of harmonic function, you require these results. So now let us move to solve some examples based on this topic, analytic functions. In the first example, we are going to use the condition that the given function is analytic, and we are going to find the constants a, b, c and d. So the procedure is very simple. First write the function given in the example, identify real and imaginary part of the function, that is u of xy and v of xy. Then find the four partial derivatives ux, uy, vx, vy using the derivative formulae and the partial derivative concept. Then, since here it is given that the function is analytic, so the CR equation should be satisfied, means the four partial derivatives should be in this form, ux equal to vy and uy equal to minus vx. Now you are having already these four partial derivative results. Just use this condition and equate the corresponding results. Here, comparing the similar terms on LHS and RHS, we get d equal to 2, and comparing the y terms, we get a equal to 2. Similarly, for this second pair of ratios or second pair of equations, we get a equal to minus 2c and 2b equal to minus d. So, using these four results, you can easily find out the values of a, b, c and d. So, in this way, we can apply the CR equation results if the given function is analytic to find the values of the constants. So, these are the favorite examples of the paper setter as far as your university exam is concerned. Determine m such that the function f of z 1 by 2 log of x square plus y square plus I tan inverse mx upon y is analytic. Again here the same procedure you have to apply as in case of example 1. Just we have solved that example. Write the function given in the example. Identify u of xy and v of xy. Then find the four partial derivatives using the partial derivative concept and the differentiation rules, differentiation formulae. Then use the given condition that the function is analytic and CR equation should be satisfied. Write the CR equations. Write the results which you have got. Now comparing LHS and RHS in these two equations, we get the value of m as minus 1. So comparing the similar terms, we get m equal to minus 1. Either you consider this pair of ratios or this second pair of ratios. You will get the same answer, that is m equal to minus 1. Let us move to the next example. This is also very important example, but this example or such type of examples are not frequently asked in university exams, but you should know the procedure to solve such type of examples. So what is given here? Already a function is given it is given that z is not equal to 0 and a functional value at 0 is equal to 0. But you have to show that this function is not analytic at the origin, that is at 0 0, means at x equal to 0 and y equal to 0, even though it satisfies CR equations at the same point, that is at the origin. So first write the given function as it is. Let us separate the real and imaginary parts of the function by actual multiplication in the numerator. So identifying u and v and then finding its derivative, you can solve this example. But to find the derivative, the partial derivative of u and v with respect to x and y, here we are going to use the basic formula, or you can say basic definition, that is in limit form. So using this definition, you can easily find the 4 partial derivative results, and you will get that the 4 partial derivative results are same, that is equal to 0. So from these 4 results, it is clear that the CR equations in Cartesian form at the origin, that is at the point 0 0, are satisfied. Now we have to show that the function is not analytic. Function is analytic if it is having the derivative, unique derivative at each and every point of that region. Now we are going to prove that this function is not analytic, means we have to prove that it is not having unique derivative. So let us start this second part. So first find out the derivative of the function at the point 0 0, that is at origin. So again here use the definition or formula of derivative in limit form. So simplifying, that is using the value of f of 0 at 0 as given in the example, we get this simple limit. Here put f of z as it is, and this z is nothing but x plus iy. So simplifying this one, we get this limit as z tends to 0, x cube y raised to 5 upon x raised to 6 plus y raised to 10. Now we are going to use different values or different relations between x and y, that is we are going to find the derivative of f of z at origin along different paths. So let us apply the first path. If z tends to 0 along the path y equal to mx, then find the value you will get for this limit. Let us check this limiting value. Here along this path y equal to mx, means you have to write each and every y in this result as mx. So with this, along this path or with this y equal to mx, we get f dash of 0 as 0. So this is f dash of z at origin, which is equal to 0 along this one of the path y equal to mx. Now let us check whether we are getting the same derivative value along another path or not. So along this second path y raised to 5 equal to x cube, we get the derivative value as 1 by 2. So from this it is very clear that along different paths we are getting f dash of z at 0, that is at origin, different values. So that is the limit depends on the path, and hence f of z is not analytic at z equal to 0, that is at the origin. So in this way we can solve such type of examples, but the frequency of such type of examples in exam paper is not more than 10%. So you should know this example. Now some important examples. Here we are going to find derivative also. So this is the additional part as compared to the first 3 examples. Here we are going to show that the function is analytic, means it should satisfy CR equations, and with this we are going to find its derivative. So let us go to the solution. Here sine hyperbolic z is given. So to find the real and imaginary part, you have to replace z by x plus iy. Then using sine of h of x plus iy at sin hx cos y plus I cos x sin y, that is the result from hyperbolic functions, You can easily identify real and imaginary functions u and v. Find their derivatives. 4 partial derivative results you will get. Now check whether these cross results are equal or not, that is ux equal to vy, and these two results should be negative of each other. So here the CR equations are satisfied, and hence we can say that this function f of z is an analytic function, and also these 4 partial derivatives are continuous partial derivatives. So with these two conditions satisfied, we can say the given function is an analytic function. Now the part left is to find its derivative. So the formula to find the derivative is dou u by dou x plus I dou v by dou x. We are having already these two results, so just use these two results over here, and again applying the results from hyperbolic functions, you will get that the derivative of sine hyperbolic z is simply cos hyperbolic z. So in this way, along with the function to be proved as analytic function, you have to find its derivative. Now let us move to the next example. Very similar example. Here function is given as log z, and we have to find its derivative also. First part is to prove that the function is analytic. Since here log function is used or logarithmic function is used, we are going to use exponential form of the complex number z, which is nothing but r e raised to I theta. So using or applying laws of logarithm, we can simplify this function as log r plus I theta. So u equal to log r and v equal to theta, these are nothing but the real and imaginary parts of this function w. Now here we have to find the 4 partial derivatives with respect to r and theta. So from these derivative results, check whether the given function is analytic or not. For this you have to use the CR equations in polar form. So the CR equations in polar form are dou u by dou theta equal to minus r dou v by dou r, and dou u by dou r is equal to 1 upon r dou v by dou theta. So from these 4 results of partial derivative, these two equations, CR equations in polar form, are satisfied, and hence we can say that this given function is analytic function. Now we have to find its derivative. Here in case of polar form, the formula to find the derivative is different one. Remember this formula. It is not only dou u by dou r plus I dou v by dou r as in case of Cartesian form, but along with this there is a multiplier, that is e raised to minus I theta. So substitute the results. Already you are having these results. Now substituting these results and simplifying, you will get that derivative of log z is 1 upon z. So this is the example where we have proved that the function is an analytic function, and also we have obtained its derivative. Now this 6th example is very similar to the first example. Here the function f of z is given in polar form, that is in terms of r and theta, and it is given that the function is analytic, but one constant is used and you have to find its value. So this example is very similar to the example number 1 of this video, where we have obtained the values of the 4 constants a, b, c and d. So we are going to follow the same procedure here also. So first write the function, identify u and v, find the 4 partial derivatives, and then since the function is analytic, you can use the CR equation. Both the equations, put the obtained results, and comparing you will get the value of p as 2. So you can compare this pair of equations or this pair. So everywhere you will get the same value of p, that is p equal to 2. So these are some of the favorite examples of the paper setter. As far as this introductory part of analytic functions from the unit of functions of complex variable is concerned. So try to solve these examples independently and also try to solve such type of examples from your textbook and enjoy learning. Thank you very much for listening patiently. Have a nice day.